Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12 physics, get more than 95% marks, electromagnetic induction, chapter 6, NCERT line by line, part 5. Before we start our today's class, we have a humble request. Please subscribe our channel if you have not done yet. Please like and share our videos among your friends and relatives. Please click on the bell icon so that you will not miss any of our videos, because after clicking on the bell icon you will get automatic notification whenever a new video is uploaded by us. Let us begin today's class. 6.8 Eddy currents. So far we have studied the electric current induced in well defined paths in conductors like circular loops. Even when bulk pieces of conductors are subjected to the changing magnetic flux, induced current are produced in them. However, their flow patterns resemble swirling eddies in water. This effect was discovered physicist Foucault, and these currents are called eddy currents. So let us understand the first paragraph. So till now we have studied about the induced current, induced EMF and then induced current. So if we piece a bulk pieces of conductor and they are subjected to changing magnetic flux, then induced currents are produced in them also. But the flow pattern resembles like swirling eddies in water. Swirling eddies means like if you throw a stone in a pond, what will happen? The ripples will form. And you understand swirling is like ripples, and eddies. Eddies are like small whirlpools. Okay. Uh, so if you have seen whirlpool in water, sometimes you can see in the oceans, videos in YouTube's in oceans and seas, sometimes in big lakes. So the pattern of this current is like this, like a swirling eddies. So uh, this current was known as eddy. So therefore this current was known as eddy current. Okay. Now consider the apparatus shown in figure 6.13. Here 6.13. These are the apparatus. Fine. A copper plate is allowed to swing like a simple pendulum between the pole pieces of strong magnet. It is found that motion is damped and in a little while the plate becomes to halt. The plate comes to halt in the magnetic field. We can explain this phenomena on the basis of electromagnetic induction. Magnetic flux associated with the plate keeps on changing as the plate moves in and out of the region between magnetic poles. The flux changing induced eddy current in the plate. Direction of the eddy current are opposite when the plate swings onto the region between the poles and when it swings out of the region. If rectangular slots are made in the copper plate as shown in the figure 6.14, then area available to the flow of eddy current is less. Thus, the pendulum plate which holds or slots reduced electromagnetic damping and the plate swings more freely. Note that the magnetic moments of induced current which opposes the motion depends upon the area enclosed by the current. Recall equation M is equal to IA. So let us understand this. So consider this magnetic pole. This is north and this is south, and a plate, copper plate, which swings like a pendulum. It goes here, here, again it comes back, again it goes to and fro. It moves like a simple pendulum, and as soon as it moves into the magnetic field, and it its magnetic flux changes. As soon as the magnetic flux changes, the current is induced in this plate, in this copper plate. Since the current induced always depends upon the area of the current flows, here the area is little less. Area of the eddy current flowing is little less. Let us move forward. Let us see what the next paragraph is telling. This fact is helpful in reducing eddy currents in the metallic cores of transformers, electric motors, and other devices in which a coil is to be wound over metallic core. Eddy currents are undesirable since they heat up the core and dissipate electric energy in the form of heat. Eddy currents are minimized by using lamination of metal to make metal core. The lamination are separated by the insulating material like uh, lacquer. The plane of the lamination must be arranged parallel to the magnetic field so that they cut across eddy currents path. The arrangement reduces the strength of eddy currents since dissipation of electric energy into heat depends on the square of the strength of the electric current, heat loss is sustainably reduced. Eddy currents are used to advantage in certain applications like first, magnetic braking in trains. First application where it is used, uh, magnetic braking in trains. Strong electromagnets are situated above the rails in some electrically powered trains. When the electromagnetic magnets are activated, the eddy currents induced in the rail oppose the motion of the train. As there is no mechanical leakage, the braking effect is smooth. So what happens? Strong electromagnets are situated above the rails in some electrically powered trains. When electromagnets are active, the eddy current induced in the rail oppose the motion of the train. As there is no mechanical leakages, the braking effect is smooth. Second, electromagnetic damping. Certain galvanometers have a fixed core made of non-magnetic metallic material. When the coil oscillates, eddy current generates in the core oppose the motion and bring the coil to rest quickly. Third is induction furnace. Induction induction furnace can be used to produce high temperature and can be utilized to prepare alloys by melting the constituent metals. A high frequency alternate current is passed through the coil which surrounds the metal to be melted. The eddy currents generates in the metal produce high temperatures sufficient to melt it. Fourth one is electric power meters. The shiny metal disc in the electric power meter analog type. Which type of meter? Analog type. Rotates due to the eddy current. Electric current are induced in the disc by magnetic field produced by sinusoidally varying current in a coil. You can observe the rotating signing disc in the power meter of your house. So these are the some of the applications of eddy current. So now we'll start with 6.9 inductance. An electric current can be induced in a coil by flux change produced by another coil in its vicinity or flux change produced by the same coil. So electric current is induced in a coil by changing the flux either by the same coil or by another coil. These two situations are described separately in the next two subsections. However, in both the cases, the flux through the coil is proportional to the current. That is, phi b is directly proportional to I. Further, if the geometry of the coil does not vary with the time, then delta phi b upon delta t is directly proportional to delta I di by dt. d phi b by dt is directly proportional to di by dt. For a closely wound coil of n turns, the same magnetic flux is linked with all the turns. When the flux phi b through the coil changes, each turn contributes to the induced EMF. Therefore, a term called flux leakage is used, which is equal to N phi B for a closely wound coil. In such a case, N phi B is directly proportional to I. The constant is proportionality. In this reaction, is called inductance. In this relation is called the constant is proportionality. In this relation is called inductance. So this is called inductance. So let us go through this again. So change in flux is directly proportional to the current, induced current, of course. Again, rate of change of flux is change of rate of change of the current is directly proportional. to rate of change of current. For a closely wound coil of n turns, the same magnetic flux linked with the turn with all the turn. When flux phi b through the coil changes, each turn contributes to the induced EMF. Therefore, a term called flux flux linkage is used, which is equal to n phi b. Flux linkage is used, which is equal to n phi b. N phi b is proportional to I. The constant of proportionality in this relation is called inductance. We shall see that inductance depends only on the geometry of the coil. And intrinsic material properties. This aspect is akin to capacitance, which for a parallel plate capacitor depends upon the plate area and plate's separation geometry and dielectric constant K of the intervening medium, that is intrinsic material property. Inductance is a scalar quantity. It has a dimension of ml2 t minus 2 a minus 2. The SI unit of inductance is Henry. SI unit is Henry and it is denoted by H. It is named in honor of Joseph Henry, who discovered the electromagnetic induction in USA independently of Faraday in England. Now 6.9.1 mutual inductance. Consider figure 6.15. So this is the figure 6.15 where two coaxial solenoid of same length L are shown. So one is this one, bigger one, and this is S1 and this is S2. Number of turns in S1 is N1, number of turns in S2 is N2. The radius of small solenoid is R1, the radius of bigger solenoid is R2, and this is the figure. Now let us go back. Consider figure 6.15, which shows two long coaxial solenoids each of length L. We denote the radius of the inner solenoid S1 is by R1 and the number of turns by unit length per unit length by N1. The corresponding quantities for the outer solenoid S2 are R2 and N2 respectively. The N1 let N1 and N2 be the total number of turns of coils S1 and S2 respectively. When the current I2 is set up through S2, it in turn set up a magnetic flux through S1. Let us denote it by phi 1. The corresponding flux leakage with solenoid S1 is N1 phi 1 is equal to M12 I2. This is equation 6.9. M12 is called mutual inductance of solenoid S1 with respect to solenoid S2. It is also referred to as the coefficient of mutual inductance. For these sample coaxial solenoids, it is possible to calculate M12. The magnetic field due to the current I2 in S2 is mu 0 or mu naught also we say instead of mu 0 N2 I2. So this is the magnetic field. The resulting flux linkage with coil S1 is N1 phi 1, N1 is capital N1 is N1 number of turns into length, and phi 1 is area pi r1 square, and the magnetic field is mu naught n n2 L2. So ultimately we get mu naught n1 n2 pi r1 square L I2. This is the equation. This is equation 6.10. Now again let us see this equation. So when I2 is set up through S2 coil, it turns it in turn set up a magnetic flux through S1. So it set up a magnetic flux through S1. When I2 is passed in S2, it set up a magnetic flux in through S1. Thus, it is denoted by phi 1. The corresponding flux linkage with the solenoid S1 is N1 phi 1 is equal to M12 I2. M12 is called mutual inductance of solenoid S1 with respect to solenoid S2. It is also referred as the coefficient of mutual inductance. Coefficient of mutual inductance. For these simple coaxial solenoid, it is possible to calculate M1, M12 or coefficient of mutual inductance. We can calculate it. The magnetic field due to the current I2 in S2 is mu naught N2 I2. The resulting flux linkage with the coil S1 is N1 phi 1, N1 capital N1 is equal to capital, so you have to understand here. So capital N1 is equal to N1 the number of turn into the length, and again phi 1 is equal to mu naught N2 L2, mu naught N2 I2, mu naught N2 and I2. You have to remember this. Phi is equal to. So if we want to find the linkage, flux linkage, flux linkage is equal to N1 phi 1, and put the values this value together, you will get the N1 phi 1 will be equal to N1 L, then area will be equal to pi r1 square. After that, the magnetic field will be equal to mu naught N2 L2. If we multiply everything, then we get mu naught, then N1 N2 pi r square r1 square L I2. This whole thing we get. Now when N1 L1 is the total number of turns in the solenoid S1, thus from equation 6.9 and 6.10 we have M1 M12 is equal to mu naught N1 N2 pi R1 square L. So similarly we have this one. So next, so here mutual inductance. Mutual inductance. So this is equal to M12 multiplied by I2. So if we want to find out M12, the mutual inductance, it will be mu naught N1 and 2 pi R1 square L I2 upon I2. I2 and I2 gets cancelled. So we got is equal to mu naught N1 and 2 pi R1 square L. This is the value of mutual inductance. That's it. Now that we neglect the age effect and consider the magnetic field mu naught N2 I2 to be uniform throughout the length and width of the solenoid S2. This is a good approximation, keeping in mind that the solenoid is long, implying L is much greater than R2. We can consider the reverse case. A current I1 is passing through the solenoid S1 and the flux linkage with coil S2 is N2 phi 2 is equal to M21 I1. So same like equation 6.9, we can write here oppositely. N2 phi 2, here we have written N1 phi 1 is equal to M12 I2. Here N2 phi 2 is equal to M21 I1 in the same way. So M21 is called mutual inductance of the solenoid S2 with respect to solenoid S1. The flux due to the current I1 in S1 can be assumed to be confined solely inside S1 since the solenoid are very long. Thus flux linkage with solenoid S2 is N2 phi 2 N2 L pi R1 square mu naught N1 I1. Same way we have derived the previous one, and where N2L is the total number of turns in S2 from equation 6.12, we can write M21 is equal to mu naught N1 and 2 pi R1 square L. Same way we have derived previously. Equation 6.11 and 6.12, we get M12 is equal to M21, that is M. So here if we here you can see M12, M12, this equation, or directly we write this one, is equal to M21. M21. So M12 is equal to M21 is equal to MC. If we demonstrate this equality for long coaxial solenoids, we have demonstrated this equality for a long coaxial solenoids. However, the relation is far more general. Note that if the inner solenoid was much shorter and placed well inside the outer solenoid, then we could still have calculated the flux linkage as N151 because the inner solenoid is effectively immersed in uniform magnetic field due to the outer solenoid. In this case, the calculation of M12 would be easy. However, it would be extremely difficult to calculate the magnetic flux linkage with the outer solenoid, as the magnetic flux due to the inner solenoid however vary across the length as well as cross section in the outer solenoid. Therefore, the calculation of M21 would be extremely difficult in this case. The equality M12 is equal to M21 is very useful in such situations. In which situation? When M21 is very difficult to calculate. So we know that M12 is equal to M21, therefore we will calculate M12 and we'll say that since both are equal, so the value of M21 is same. Okay. We explained the above example with air as a medium within the solenoid. Instead of medium, relative permittivity mu r had been presented and mutual inductance would be, so if we have mu r relative permeability, then mu r will be multiplied to the whole result for m. So it is also important to know that the mutual inductance of a pair of coil solenoids etc. depends on the separation as well as its relative orientations. So it depends upon their separation as well as relative orientation. What? Mutual inductance of a pair of coil or solenoid. Now let us do example 6.9. Two concentric circular coils, one is smaller radius R1 and other larger radius R2, such that R1 is much smaller than R2, are placed coaxially with centers coinciding. Obtain the mutual inductance of the arrangement. Let the current I2 flows through the outer circular coil. Filled The field at the center of the coil is B2, that is mu naught I2 by 2R square. Since the other coaxial field, coaxially placed coil uh, is has a very small radius, B2 may be considered constant over the cross section area. Hence, phi 1 is equal to phi 1 is equal to pi R1 square B2. Pi R1 square B2 is equal to pi r1 square b2. So instead of b2 we can write mu 2 pi r1 square upon 2 r2 square multiply by I2. So we have put this value here and we get this. So instead of so instead of this we can write, which is equal to m12 multiply by I2. So we know phi 1 is equal to m12 I2. So instead of phi 1 we can write m12 I2. So actually we got phi 1 is equal to mu naught pi r1 square upon 2 r2 square I2. Again, instead of phi 1 we can also write m12 I2 is equal to the same value mu naught pi r1 square I2 upon 2 r2 square. So I2 gets cancelled. So m12 pi mu naught pi r1 square upon 2 r2. There's no risk square here. So 2 r2. and m since 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 m12 is equal to m21, therefore m21 will also be equal to mu naught pi r1 square to r2. Now, so we got this value here. Note that we calculated M12 from the approximate value of phi 1, assuming that the magnetic field be to form uniform over the area pi r2 r1 square. However, we can accept the value because r1 is much less than r2. Now let us recollect experiment 6.3 in section 6.2. In that experiment, EMF induced in coil C1. However, there was any change in the current through the coil C2. Let phi 1 be the flux through C1, say N1 turn, when the coil C2 is current in the coil C2 is I2. From equation 6.9, we have N1 phi 1 is equal to M I2 for the current varying with time delta or d N1 phi 1 upon dt dm I2 upon dt. Since induced EMF of the coil C1 is given by d N1 phi 1 upon dt, so we can write E1. E1 is equal to minus m di2 dt di2 dt. It shows that varying current in the coil can induce EMF in the neighboring coil. The magnitude of the induced EMF depends upon the rate of change of current and mutual inductance of the two coils. So this is a very important relation. Let us keep this class till here. In the next class, we'll go through self-inductance, which is again a very important concept and very easy lesson and interesting lesson. Before ending today's session, we request you to subscribe our YouTube channel if you have not done yet. Please click on the bell icon so that you can get automatic notification whenever a new video is uploaded, and there will be no chance that you will miss any of our videos. And please like and share our videos among your friends and relatives so that they can also get benefit of these free videos. Thank you very much for watching our videos and supporting us. Thank you.